Welcome to another episode of the ASEF Podcast. I'm Tanja Janko, host of the science vertical of the ASEF Podcast. This season, we will be exploring the theme of emergent patterns and complexity and how simple interactions can give rise to incredibly complex systems we see in nature, technology, and society. Today, I'm very happy to welcome Lee Cronin. He is a professor of chemistry at the University of Glasgow. Lee is one of the leading developers of assembly theory and the creator of Chemputer, which is a platform that is designed to digitalize and automate chemical synthesis. And his work is really addressing a profound question, which is at what point does ordinary chemistry become life? Thank you very much for joining us, Lee.
It's nice to be with you.
I would like to begin with a kind of conceptual distinction that seems to appear across many fields, and also something that I have mentioned in the title of the season. It has also been kind of an inspiration of the season. So I want to ask about distinction between patterns and codes. So in physics, we often see patterns emerging naturally from simple laws, things like crystal structures, snowflakes, or galaxies. But biology seems to introduce something that looks like codes, so DNA, for example, which is not just kind of a repeating pattern. It is a symbolic sequence that gets translated into proteins by cellular machinery. So do you think that life represents a transition where chemistry begins to produce something like codes, or is the distinction between patterns and codes something misleading?
That's a very deep question. I think it depends on your ontology. Mm-hmm. Now, if your ontology is that the universe is some kind of computer, and you have some kind of coordinates and memory, then the patterns to code things kind of make some sense. Mm-hmm. But what is really happening is a bit different in that we see patterns in the environment because they're regularities within the combinatorial space. But actually, because the universe doesn't have a memory, we can only look at these recurring conditions. And we often get ourselves into a tangle of what we mean emergence and complexity. So I think that selection produces the appearance of a code, and that happens through error correction. And I guess a code is present, but there had to be a certain causal history to make that code emerge and then allow it to be transmitted between objects that have evolved that code. And that is a little bit different from this idea of a freestanding Platonic code, because there is no Platonic universe.
So I thought that this would be kind of like a good entry point into assembly theory. This is obviously, I think, like the most important thing that you're working on. Not of course to say that the rest of the things that you're working on are not important, but this is also something that will be like the big thing of today's podcast and conversation. So the central idea in your work or in assembly theory is that molecules carry traces of how they were built. So assembly theory introduces the concept of assembly index, which measures the minimum number of steps needed to construct a molecule from reusable pieces. So instead of just continuing counting atoms, you're really measuring the complexity of how the structure came together. So at the beginning now, I would just like to ask you if you can explain assembly theory, how you came up with assembly theory, and you often use, or I heard you use Lego analogy to explain it, and I think that is really useful. So if you could maybe repeat that would be great.
Yeah, for sure. I think assembly theory, where it is now, is really trying to explain how causation exists in physics at the bottom, where people really don't think it's there. And I think it is a really good way, as you said, to basically explain how I came up with it. So really, assembly theory was born as the idea to say, can I tell the difference between a system that was created by biology or something that just occurred randomly in the environment? And that, I think, is super interesting because it seems like a almost trivial problem to start with. But many people think that complex objects could spontaneously emerge. And that is indeed true. But we never really see them in any high number to count. So when an object has to emerge, in a complex, any complexity, it has to have a copy number. So when I basically asked the following question, which is the way I came up with assembly theory was to basically tell the difference between objects that were created by evolutionary processes or technology or random. And the way to do that is just to say, well, how many parts does this object have? What is the lack of symmetry? And to give you a really nice analogy, you talked about in the beginning, like a snowflake. We find a snowflake that is perfect apart from some defects along a certain spine. The chances of that snowflake are reoccurring again will be very, very low as a function of the number of defects, right? But if I was to give you 1,000,000 snowflakes with exactly the same defect, and let's say I was able to write your name in the snowflake, in the deflect, in some kind of Morse code or something, you'd be like, whoa, something produced that snowflake, right? It's not just a normal snowflake. And that's where kind of assembly theory got born, because I figured that we could actually measure these types of snowflakes. In this case, they were molecules, but made out of atoms and bonds. And that's where the Lego analogy comes from. And it's very simple. Like, the more different Lego pieces that needed to come together, the more difficult it is to build the molecule, and the more history that must have passed and the more memory. And so that was kind of phase one to assembly theory. There are 3 phases to it that I can talk you through, but I'll just pause there. So just to answer your question and bring in the Legos. And the assembly index is the minimum path, the minimum number of steps you need to produce that object. But then there's another critical part, which is the copy number. So the assembly index tells you how chancy it is. The copy number says how weird it is, right? Because if you have 1,000 Lego, I don't know, Harry Potter kind of castles, and you find them on Mars, you're going to be like, well, who put them here? Whereas if you found 1,000 Lego blocks that didn't form anything, you'd be like, well, maybe that was just a random event. And so we have the complexity index, or I prefer to call it the assembly index, because complexity doesn't exist only in computer science, and the copy number, the number of objects. So that was the first phase of me kind of building assembly theory, because I did it as a thought experiment from an experiment I would do in the laboratory.
So you propose that molecules that are under the assembly index of 15 are unlikely to produce biological processes. Why is that, and why number 15?
So it was merely an experimental observation. So to start with, to test this, we had this idea. The idea was complex molecules with a high assembly index, that is, and high abundance, wouldn't form naturally. So we got a whole bunch of samples from NASA and other lab, and we basically did a load of measurements on these samples. And these samples covered a number of categories. They just were dead samples, living systems we had killed, burnt, stuff from the environment, from the desert, no life there, old fossils, different ages, and living ones, and living samples. And in all the cases of all the living samples and the fossils, you could see molecules with assembly index of 15 and above. There was a massive lot of them. With all the stuff that we had burnt, sterilized, or taken from the desert, you couldn't get beyond about 12 or 13. So there was actually a gap between what biology was able to produce and where inorganic random chemistry ended. And we just concluded that was kind of the limit of complexity on Earth outside of biology. And it was just an observation to say, well, this is an actual observation we've got. What we've done recently is we've actually got some theoretical justification for that barrier, which is really exciting, which is intrinsic to how organic chemistry on Earth works and the processes that undergo evolution. But it was just an observation. And when we saw it, we're like, oh gosh, there is a gap between living and dead samples. And that got us very excited.
How many samples did you sample to make a conclusion?
Several hundred. It's now several thousand, and also some of the samples were double blinded by NASA.
Oh wow!
Because they didn't believe that we would. They tried to basically confuse us with meteorites, because some meteorites have really complicated molecules, or they weren't complicated. They were a complex mixture of molecules with lots of different isotopes that you wouldn't find on Earth. And that meant the weights were all ever so different. And NASA were wondering if our algorithm would cope with that. And it did. And they were pretty excited when it passed the test.
And do you maybe want to explain to our listeners how exactly you perform the analysis? I assume you use a mass spec, right?
Yeah, for sure. So what we did is we had a standard procedure where we would take the sample, suspend it in a solvent, and then try and dissolve it, and then extract it, and then put it into a mass spec. In this case, we used a very sensitive and sophisticated mass spec called an Orbitrap. And what it does is the molecules can't go in, are sprayed in, charged, and they go into what's called an electrostatic trap, an Orbitrap, where they get put into an orbit. And that allows us to weigh them, but then fragment them. And what you can do is you can fragment them in steps. So you can hit the molecule and fragment it, and then look at the daughter peaks. And then you can fragment the daughter peaks, and then look at those peaks and carry on. And that ability to do mass spec is a bit like taking a molecule and cutting it up, and then cutting up the fragment, and then carrying over the fragment, and cutting it up. And it's kind of analogous to the assembly pathways where you try and break the molecule from the complicated part into smaller parts and reconstruct them. And so the mass spec experiment unwittingly was doing exactly what the algorithm did when we were numerically calculating the assembly indices on the graph. So when we got a strong correlation between the two, it was of no surprise to me, although some from my team are still confused by it. But that was the experiment we did. So, and that was with blinded samples where we didn't know what the molecules were. Of course, we had got molecules where we knew what they were and got calculated the assembly indices using the graph of the bonds in the molecule because the molecules, but we also then took it in the mass spec and took a measurement, and were able to show what we were able to calculate and what we were able to measure were correlated. And that gave, and we started to then do statistical tests to make sure that correlation was causal and not spurious.
And mass spec is also one of the instruments that goes on rover and is then sent to Mars, for example, or to be using mass spec to search for biosignatures on potential other planets. Do you think that your theory would be a good way to then detect potential life on other planets? And what, in that context also, how many replicates or copies of this complex molecule do you think we would need to say there is life on other planets?
Yeah, so we would love to send mass specs with the right resolution, the ability to do this kind of sophisticated cutting, and they're getting there. There are mass specs on Mars right now, right? We could do mass specs, but there is a mass spec going to be sent to Titan on a nuclear-powered drone, believe it or not, called Dragonfly, which we can talk about, which is super exciting. And I think that although we may not get definitive data because it might not have enough resolution, we'll be able to get a good hint. Now, very good thing, when you do a mass spec experiment and you make an observation, it's not just one molecule. You have to accumulate tens of thousands of identical molecules. So as long as you get a decent signal, you should be able to say what if something was definitive or not. But of course, in science, when we're doing things remotely, we have to be a little bit more careful, because the sensationalism with finding aliens is kind of hilarious, right? Where everyone's discovering aliens. So the way I would do it would be to say, hey, we're going to take our robot mass spec, collect samples, characterize the background, and then almost go sniffing to say, oh, we smell some complexity in the mass spec, and we just go closer to the target and see if the indicator goes up. And then when we get to the point where we find lots of high assembly index molecules in high abundance, we'll maybe take some photographs or take a sample and see if we could see evidence of microbial life or something. That would be super cool. The other thing is you go around the planet and take different samples because, although we see on Earth the cutoff seems to be 13 and 15, what on Titan? Titan's really cold. Titan's got different type of chemistry. Maybe the threshold in chemistry on Titan is lower because there's not that much energy, and evolution has to do a lot more work, right, to get even to modest complexity. We just don't know. And I think what we want to be able to do is say, well, look, what would be a absolute certainty or a 99.9% life protection, well, that would be probably assembly index of 50, right? That would be amazing. And what would be exciting would be anything between 10 and 15, right? And that would be super exciting. So we've got quite a wide range to look at. And what I would do if I was an instrument developer is I would bring some smelling salts along on the robot where I put some molecules there where I know that they're high assembly index, so I could calibrate and check. So every time I open up the box and smell the complex molecules, I could check the machine was working, right? There's lots of problems with that because people would say you might contaminate your instrument and all that stuff, but of course you can measure the background. So I think it's possible we can do that, but there's an even more interesting prospect in that you can actually not just use mass spec to count the number of parts, but you can also use infrared spectroscopy. And this means you might be able to start to use a James Webb telescope to look for exoplanet atmospheres and find life in the atmospheres.
Exciting. So many prospects for searching life on other planets.
And it doesn't have to involve UFOs and random UAPs and conspiracy theories, but we can do that as well. We can say what the assembly index of the alien abduction is. That's a joke.
So I also wanted to talk about chirality. So many molecules can exist in two mirror image forms, so left-handed and right-handed. But one of the most interesting facts about life is homochirality, so one-handedness. So proteins use almost exclusively L amino acids, and many biological sugars are in D forms. And in abiotic chemistry, so the chemistry that happens without life, without living organisms, we often find a mixture of both. Once life emerged, one-handedness seemed to have been repeatedly amplified and locked in. So do you think that homochirality could be understood as early example of kind of historical selection that assembly theory is trying to detect?
For sure, I think so. I think that chirality was not required at the origin of life, but competent life had to produce chirality. And there seems a way more plausible thing that had to happen. Although that's a very contentious statement, but I'm very good at making contentious statements, apparently, I keep being told. But it seems to me, if the universe seems to be roughly equal, and the only place where we find excess is where there's biology, the obvious answer is biology did it, I would say. But I'm just a simpleton when it comes to that type of science, right?
I will say that while researching assembly theory, there's also lots of critics. So your theory relies on abundance, so finding many identical copies of complex objects. And critics have asked whether assembly theory is closely related to ideas like compression or Shannon entropy, which measures how much information or randomness there is in a system. How would you respond to that?
Oh, yeah, it's really simple, right? So, of course, assembly theory is looking at the shortest path. So one way of looking at it is saying it's compression, but it's not really doing that. It's really doing an expensive compression, right? And so the first thing I would say is that there's kind of one or two critics in this area, and they don't really understand the ontology for the theory. And I think so, yes, many theories look like X. And I think that, I don't know what happened. It was kind of a really weird sociological experiment. So the ontology of assembly theory is there's stuff at the base. And so what is ontology for any theory means what are the parts? So you have to have building blocks, and you have to have the assembly index, and you have to have the shortest path. And the shortest path on a graph gives you a history. And that causal history is what the critics keep ignoring, because they don't really understand it, because they keep trying to see it through a low-dimensional lens. And that's kind of like my really, it's like, sure, it looks like compression. But the other thing that's really interesting is the Shannon entropy and compression are in different complexity classes to the mathematics of assembly. So when people try and say they're the same, I'm like, but the mathematics is a different complexity class. So what are you talking about? And they kind of ignore that and just say something else. But what is really important, I think, is the ontological argument. It's like, who cares what a theory is like? What is a theory trying to do? What problem does it solve, right? And I think that I have no problem. In fact, I'm a better critic than all my worst critics because I actually criticize the theory properly and say, well, what if we've confined a high abundance of a complicated molecule in the environment without life? That would falsify the theory, right? And so the critics are actually fall into a number of classes, and there's not that high a number. There are some people from evolutionary biology that are misunderstanding how we use the word selection. So that's easily corrected because selection did occur before biology. There are some people in origin of life chemistry who are curious about how we can use it to help get to network and so on. That's great. That's really positive. But there's one or two computer scientists who basically said it's compression. And they kind of, because they have this complex where the universe is a computer and everything is a program. But we have no data to substantiate that. But we have lots of data to substantiate the idea that life produces complex molecules, right? And so I would say, sure, comparing it to Shannon entropy requires an encoder and a decoder. So where did the encoder come from? Was it God? Right? And where does compression come from? Someone had to write the compression algorithm. God again? So really, the only real critics I've seen of assembly theory are, number one, the creationists, and number two, one or two computationalists who share this same kind of religious complex. And it's kind of funny because it's like, yeah, sure, it's not serious. But I'll make another really interesting fundamental argument, which is like, in computer science, there is this thing called Kolmogorov complexity. And Kolmogorov complexity, simply put, says, hey, if I write a program and the program does a thing, what is the shortest way I can describe that program to do the thing, right? And looking at the number of parts of that program. And the size of that program is what we call the Kolmogorov complexity. Now, the problem with Kolmogorov complexity is you cannot actually calculate it precisely. You can only do it approximately. Why? Because the program is in a language, and that language could have hidden complexities in it. So whilst in one language you could write a program of one length, in another language the program might be a longer length. And so that Kolmogorov doesn't tell you anything about the actual causal structure because it's not relative. Whereas in assembly theory, it says, hey, we don't care about that. We care about what is the minimum number of causal constraints that give us the thing, and which is why we get this assembly index, shortest path, abundance, and the assembly equation, which is not a heuristic. It is a derived equation from the mechanism assembly theory. And so, yeah, the computationalists and the creationists are the same camp. And I just say, good luck. What I would like people to do is to give me proper criticism, which is falsifying the theory, because assembly theory, of course, is not the end. But assembly theory right now seems to provide a metrology for causation and also to tell the difference between life and non-life, and that will help us go further. And I think the people who are criticizing me doing science are not real scientists. They're just like, I don't know, they're religious creationists, but in the computer science. I'm being quite bold, but I mean, why not? It's a good question. And I would just say the first answer is like they're mathematically not equivalent. Secondly, they don't use the ontology. And thirdly, the arguments people make don't falsify the theory. So it's like, okay.
So in all of the molecules that you have screened, there was nothing that would falsify your theory? Or like so far, there was nothing that would go against it?
Exactly. And the nice thing is, right, when we find a molecule that does, and we surely must, because selection gives rise to biology. Yeah. So if we create the right environment, there'll be molecules that falsify the theory, and we're like, holy cow, what is the mechanism that's causing this complexity? Now, is it suddenly a jump? Then we'll make a discovery about how life emerges. Is it gradual? Does that mean we can see selection over time? Because when we say that, okay, the cutoff is like between 13 and 15, that's quite low. When we find that chemistry can get there, under certain conditions, we can just move the threshold and make it harder, make the speed limit faster and faster. And until the gap is so wide, it's going to be like, what is the thing that's creating that complexity? It needs to have memory. And I think this is why we're onto something really important in understanding the nature of complexity in the universe. And this, again, is the issue with the misunderstanding of complexity science born out of computer science and program resource and time resource, and then the mislabeling as the universe as a computer, and then basically applying computer science and mathematics to the universe. And what assembly theory is kind of doing is falsifying that. We're kind of saying the universe is probably not a computer, which is kind of interesting, which is maybe why that we're getting these preemptive strikes. But when we tried to publish the paper initially, the experimental paper, one professor who was a reviewer said, this is impossible. Vitamin B12 proves that assembly theory is wrong because vitamin B12 could just form in the environment. And that's just wrong. It can't. You cannot randomly make vitamin B12. The professor was mistaken. And so what we've got to do is really carefully look at the evidence. And, there's one professor who's found ATP in the environment. If that's true, that would falsify assembly theory. ATP has an assembly index of 21. But the environment in which they find ATP is either biological contamination or if they're added in reagents and the information to make it. And so it's going to be a really interesting, target. And, I love the theory because it makes a precise prediction, which is molecules with a high assembly index cannot spontaneously form. And that's something very easy to attack. Let's prove it wrong. I'm trying to do that myself in my lab at the moment.
Do you want to maybe give some examples? I don't know, something of low assembly index. Now we already said that ATP has assembly index of 21. Maybe you can give some of even higher assembly index.
Even higher than ATP, Taxol, which is a very complicated natural product, has an assembly index of 23. Vitamin B12 is, I think, something like 31. Some of the simple sugars have assembly indices of 3 or 4. And some of the amino acids, the simple ones, basically have assembly indices between 3 and 12. And then you have a transition to kind of histidine, tryptophan, phenylalanine, where they have a higher assembly index. And I don't remember precisely, I'd have to look at my amino acid chart. But a lot of the amino acids almost get to the threshold, but not quite. And then when you start to make amino acid dimers, they go above the threshold. So that means if you could find pure examples of amino acid dimers in the environment, where in a high copy number, that's going to tell you something super interesting. So that allows us to focus in the lab to say, wow, we need to make a selection engine which kind of couples a soup engine like a Miller-Urey and try and look for the production of amino acids and then dipeptides and tripeptides and show that they can form in the environment. And there are hints that these exist on meteorites.
Exactly what I wanted to bring up right now, yeah.
But the problem is, the meteorite is such a mess that you can't tell the difference between a pure sample, high abundance, and just a really large gamish. And that's really where the analytical chemistry is up against it. So I think we will get some claims of the falsification of the theory. And there's 3 potential answers to that. The first one is it's an analytical mess and wrong. The second one is just to shift the assembly index up a bit till everyone agrees that it's too high. And the third one is like, maybe selection is going on. We should take a close look and maybe that's how you get to life. And so I think that I'm excited about all 3 because I think we cannot go wrong by exploring this critically. And people that know me will know that I'm harder on my theory and my students and my collaborators doing the theory than anyone else, right? So when people criticize us, it is when people criticize you from the position of curiosity and trying to help question the science, that's a real gift. When people just criticize you because they are trying to troll you, you can just ignore them. It's easy.
Yeah, yeah, I agree. I think good constructive criticism is always there to help something to grow.
It's the most valuable thing you can give any student or professor or postdoc, right? How time starved are we? You know, everyone's looking at TikTok, LinkedIn, or whatever X. Someone actually taking the time to criticize what you're doing and give you feedback. That is like a precious gift indeed, and should not be ignored ever.
Exactly. But I think, unfortunately, we are currently more in the times where people like to give criticism before properly understanding things or even reading the whole thing through. Or
But that's fine as well. I like that too because when people criticize you spontaneously, that means they're emotionally engaged, and it means you're challenging their beliefs.
Mhm. Yeah.
And I love that as well. So basically the computer scientist or two that raised against just had their beliefs kind of shook, which is great because it means, well, we're really poking at something super interesting. If people ignore what you're doing, right, and people don't care, then you know it's not very interesting. That's why I think it's funny when some people say, well, you know, we've heard the rhetoric of assembly theory, and I'm like, the rhetoric is not a political movement. It's a theory that's very precise, and makes a precise prediction, has a precise ontology, and is relatively courageous in what it predicts. You could call it rhetoric if you want.
So, would you say that assembly theory suggests that life is mathematical inevitability?
Is life a mathematical? I wouldn't say it that way, but I know where you're coming from. I'll rephrase it. I would say that assembly theory tells me that life appears to be a physical inevitability in a universe where you have heterogeneity and sufficient resource for chemistry to occur, forming of bonds and molecules, because it seems like the combinatorial space to play in is in chemistry. I'm really excited by that because that means we can then look around the universe and look at planets that have the conditions suitable for molecular chemistry, because selection must be occurring. And hopefully we'll get lucky and find, or unlucky, depending on your view, find intelligent life and complexity of chemistry together.
I think that would be very, very exciting. Hopefully, it happens soon within our lifetimes. Hopefully, now.
I think assembly theory points the way. What I'm excited about is I think it's going to be possible for us to unambiguously detect life using instruments we're building. I do not think sociologically we're prepared, and I do not think scientifically we are prepared. But my job is not well. My job is partly that. But if I could just do the science and make it as robust as possible, be open, which is part of the reason why me and my collaborators are having these discussions, then we can get to the point where people can get adjusted to it and say, okay, there's no other explanation. Maybe it is life. And what does that mean? Because one of the reasons I want to understand origin of life in the universe or on Earth is the likelihood of life elsewhere. Then to think about what happens to life on Earth and what is life in the physical universe as a phenomena. And that's, I think, a really important thing that humanity needs to kind of grapple with.
Yeah, because I think like we don't even, we have many different definitions of what life is. I mean, there's NASA's definition and there are many others. I remember my astrobiology class and we were learning about like, I don't know, 5 different definitions. Yeah, and then obviously how, if we find a life somewhere else, how exactly to even present such a thing to the humanity, that are big questions.
You can think about gravity, right? You can have lots of different ways of defining the phenomena of gravity. But actually, what is gravity? Well, if you take the Newtonian paradigm, you can say, well, we've got two masses, they attract each other with a force that is a product of their masses and 1 over the square of the distance between them. And that's very approximately what we observe. Obviously, Einstein taught us that gravity is a bit different on that ontology. We got rid of the ontology of gravity and went to space-time, but still, we can make predictions, right? And I think what happens with life is because we're alive and we've got a blind spot, we just keep having this endless focus group. And I think we overdid it. And look, living systems are systems that are able to create complex artifacts at scale. That's the only definition you need. And that means actually a virus on Earth is alive when the virus is in the cell. when people were like often saying a virus is dead, I'm like, no, that's a wrong question. Was the virus the product of evolution? Because an astronaut in space is functionally dead because they can't have children. Astronaut has come back down to Earth to reproduce. So if you're saying the virus is dead, then the astronaut is dead. And everyone say, but no, but the astronaut is respiring and all this stuff. I'm like, well, so is the virus when it's in a cell. So I think what we have to do is kind of be much more kind of smart about what we are observing as the physical process. And of course, life is more than just the molecules in the cell, but is it? I mean, it is those molecules have a historical dependence going back to Luca, but the ability of the cell to take low complexity or low assembly index food and turn it into high assembly index objects and replicate is exactly what life does. It doesn't do anything else. That's it. Well, there's loads of other things it does, but everyone will debate it. No one will debate those two things, that living systems are associated with complex molecules in high abundance. No one will disagree with that statement. And if they do, then we need to figure out what language they're speaking, or we've seen something we don't understand.
Maybe here I can just say that in our previous season, we talked a lot about consciousness and qualia, and there is also lots of discourse where exactly this consciousness is something that is indicative of life, or it just happens in humans, animals. There's also theories of consciousness even being present in atoms, electrons. So everything has a level of consciousness. Do you have any opinions on that? Maybe
I think it's a bit like, saying the universe is a computer, right? So what is the definition of a computer, right? And then you say, well, what if you say what is the definition of consciousness? If everything is conscious and everything is a computer, then it fails to have any specific meaning. And so what I would say is to say, hey, okay, we've built computers, and computers are characterized by this kind of von Neumann architecture with a Turing machine and a labeling system. And that labeling system, we have rules, and we can manipulate those labels. And those labels allow us to do very powerful things. And we get there. Then we make a conjecture where we connect computers to quantum computers. And then we say, by extension, because everything is quantum, the universe is a quantum computer. And that actually exposes a problem with quantum mechanics we won't go into right now. Going back to consciousness, it's like, I think that it's a kind of ontology error, right? Where you're like saying, are atoms, is stuff necessary for consciousness? Yes, but it's not sufficient. The only way I know to make consciousness is the following: have some atoms in a pot on a planet and do evolution, and over time will emerge a biological organism that can basically be self-aware. And so that process is a gradual process produced by selection. Now, the fact that we share a common combinatorial chemical space, an assembly space, that we can be pretty sure that the things we feel across our lineages are very similar because we're built in the same way, what's the kind of blueprint. So the thing that we call qualia is probably a meta phenomena associated with transitions in that assembly space. So if I say to you, hey, why don't you imagine an equilateral triangle in your head? And I'll imagine it. I'm pretty sure we're both imagining an equilateral triangle or a circle. And why? Because we're both brought up in a common lineage. We're using English right now. We may have other languages in common, but and that's where all this comes from, this sensation. And I think we're trying to make sense. But what happens with consciousness is we radically mix up the levels of abstraction, which gets us confused. Like saying an electron has a degree of consciousness is a bit like saying an electron has a degree of liveliness, because it will be a living cell at some point. And so then it's I think if it doesn't help solve a problem, is predictive and doesn't explain anything, then maybe we can just call it, we don't have to use it. And so I think this is the issue I have with people talking about, say, you're talking about panpsychism.
Yeah, yeah.
And I know Philip Goff is a really nice guy. I enjoy talking to him. I don't really understand why he's a panpsychist. And I don't want to be rude about his beliefs and his commitments. But as a materialist, I am yet to understand what panpsychism does for me that physicalism doesn't already do.
Another question, or two other topics that I also wanted to cover today is you also worked on polyoxymethylates, and after that I also want to talk a little bit about Chemputer. So I found that your work on polyoxymethylates very interesting. So these are pretty much like massive metal oxygen clusters that self-assemble into complex droplet-like structures that can resemble like primitive compartments. So some of your earlier work suggests that they can behave in ways that resemble primitive cell-like structures. Could you maybe tell us a little bit more about that? And they and also the idea of the inorganic chemical cell.
Yeah, sure. I went and did a research fellowship in Germany on polyoxymethylates, and the reason I did that is that these molecules astonished me in their apparent structural complexity or intricacy. And I wanted to understand what processes drove them to produce these architectures when almost anything else could be possible. Again, it's about the combinatorial space. And so I learned a lot when I did my fellowship about the crystallography and the synthesis, and really thought about the kind of the transient conditions to try and create them. And then I started, when I was doing my academic career, I just started working on these molecules because I was fascinated and I wanted to get some credentials in being an inorganic chemist and looking at big molecules. And I think if I basically just said to everyone, I'm going to create a life form, they would be like, what? No, don't do that. And then I always thought, well, okay, the nice thing about polyoxymethylates is they're demonstratively not carbon, and they're not, because they can't be mistaken for living artifacts. So I thought, what is there a way I can generate a kind of inorganic cell to see if I can have any inorganic evolution or selection occurring? And so what I realized is POMs are very, very highly charged. So if you basically have a large cation and a small anion, you can form this mismatch where they form a membrane at the interface. And I was able to basically, make what's called a crystal garden by putting crystals of polyoxymethylates in water and adding kind of a cation to them, a salt, and they would just grow tubes. And when I saw them growing tubes, I thought, that's weird. I thought, why don't I try and make membranes? And you could push them again. They made membranes. You can make blobs. I was like, oh, wow. So you can make a membrane of a polyoxymethylates. And then when you add a battery or some electrons, you can get these gigantic clusters forming inside the cell. And I thought, well, if there's a way we could then take these cells and potentially destroy them in an environment, but give them a chance to survive by replication or adaptation or something like a Darwinian cell, I wondered if you could get a kind of like inorganic cell cycle. So that's where that work started. But it's really hard to control. And at that time, when I started the work, I didn't have assembly theory. So when I told people I was making inorganic cells that were lifelike, they were like, what are you talking about? How do you measure that? What is life? They don't have these features. And so I realized I needed to build a kind of a metrology and a theory to create, to kind of explain to people what I was trying to do in the lab, because then no one would recognize these life forms. So we'll probably go back to these actually in a few months, because they are extremely easy to manipulate and then calculate the assembly indices for them and make sure we can measure it. So that's where the idea came from. And we had the cell cycle that we had. It was an artificial cell cycle. We had to do all the work. But wherever you've got an inside, a compartment, then you're going to have selection occurring with respect to the outside. And that's what was fascinating to me.
Do you think that POMs can help us understand compartmentalization, like emerging before biology?
I think so, but they are quite esoteric and complicated for people to understand. But I think it's quite nice to say, look, hey, take some inorganic oxide and you can make membranes. Whereas the only other way to do that is have an amplifier with some lipid. But I do think making droplets with droplets stabilized with an amplifier and some lipids, kind of oil water interface, also could do that. So I think both approaches might be quite good, and might have a role in looking at selection. Because what you want to do is chemical selection is merely the selection of one set of molecules over another. And that has to happen in an environment that's different, right? And so inside of a polyoxymetallate cell or the inside of a kind of very simple lipid, they're quite dramatically different environments. So maybe we have to make a Frankenstein or a bionic life form a bionic organic life form where you've got part polyoxymetallate, part organic, and you get multiple selection happening. But I haven't done that yet. That's a good idea.
Okay. Chemputer. So this is another fascinating aspect of your work. And this is basically the idea of digitalizing chemistry. I still remember when I was in my lab, and one of the PhD students in my lab, he was really, really impressed by your Chemputer, and he was showing me your work. This is how I got to know about your work. So maybe for the very beginning, can you introduce the listeners to the idea of Chemputer and how you came up with this?
Yeah, it goes back a few years now. So I've always wanted to solve the origin of life. And then I very naively thought the origin of life was a search problem in chemical space, like Google, right? And where, like Google has the internet, just needs to search it, to find it there. And I thought, well, all I need to do is have a search engine that would search chemical space, and I would basically find the origin of life. That was so wrong, because actually the origin of life is not a search problem. It's something different. It's a possibility problem. And this is one of the reasons where I think the things I'm realizing are so beyond my intelligence. I'm just like completely unqualified. But basically, you want to go from a probability space to a possibility space. And that's kind of how evolution works. But anyway, put that aside. So, okay, I thought naively it was a search problem. So I thought I'll just get a few robots and just basically build them in my lab and just search chemical space. But I was horrified to learn that there was no standardized robotic technology. And furthermore, all the robots were really expensive. And this is just at the time where 3D printers were becoming kind of, from hobbyists were playing with them. And I was like, oh, that's cool. Why don't I get some 3D printers? They're super cheap. Well, they're expensive back then, but cheap. They're cheaper than spending $1 million on a robot. You would spend a few $1,000 on a 3D printer. And I was like, well, the 3D printer has a digital code to move the nozzle to 3D print. Here's actually a plastic item, my 3D printer. This is a Tesseract, right? But I thought I would 3D print a test tube. And I thought, cool, if I can 3D print a test tube, could I use a 3D printer to actually squirt in liquids to do reactions? And my group were like, that's crazy. And I said, no, because I have to program the 3D printer to put in the liquid. It's going to be more reliable than talking to you students, because you basically always forget what you've done. You're always drinking coffee. You're too lazy. I'm just joking, right? My students are fantastic. But what I mean is it gives you a little bit of reproducibility and regularity, but it's relatively cheap. So that's where the idea of digitizing chemistry came from. And then over the years, I realized to do organic chemistry, I needed to make it more and more extendable. And when I first said to my synthetic chemistry friends I was going to digitize chemistry, they had a vigorous and violent emotional response. And I thought it was very funny. I was like, oh, that's kind of cool. Why are you behaving this way? And they were like, oh, it's impossible. You can't digitize chemistry. You can't do that. And this was, bearing in mind, this was like 14 years ago. And so I thought, well, whoa, let's just try. And then I figured that all the robots were very expensive, too much engineering, too little chemistry, and the software was too hard to use. So I wanted to turn it around and say, could I write a software that understood chemistry? And that has taken me 10 years to do. But as of last week, the paper that presents this software and the concept, the Turing machine for chemistry, has just been accepted for publication. It will come out in a few weeks. And so the underlying physical theory for the Chemputer was born. So I built this concept 3D printer, wrote the programming language. I then went to my team and said, let's extend the programming language, do organic chemistry with it. And they were a bit grumpy. It was hard. A few years went by and we got better at it. Then the pandemic came and all the organic chemists were at home. And so, but we had the robots in the lab. So I got them to learn the language and they became really good at it, much better than me. And so suddenly they were doing this really advanced chemical reactions on the robots remotely from their houses during the pandemic. And then I realized that basically computation was going to be a big deal for chemistry. And that's why I started it, because I figured that this is a way to kind of extend further into chemical space, because computers, well, today are still mainly people. What is a computer? A computer is a thing, a person that can take a recipe and do chemistry. A computer 100 years ago was a person in a warehouse. And today a computer is just basically a silicon chip or a photonic device. So we're right now at this kind of junction, making a transition from human computers to digital computers. And for me, that's really fascinating. And I've started a company of which I'm a full-time CEO of, and it's completely exhilarating and terrifying.
So basically you're putting the chemist out of job.
No, I'm actually doing the opposite. I'm making sure that chemists have jobs forever. Why? The computer allows the chemist to be incredibly... all I've done is built the printing press for chemistry. Think about it. We spend 6 years training chemists to be incredibly creative, and then we chain them to a lab and make them do manual dangerous chemistry, and they can't make the molecules they want. What I'm doing is say, don't you do that labor. Let's design and do the hard stuff and use a robot to get there, because chemical space is bigger than outer space. And so there is no way a chemist is going to be made redundant. And this super AGI nonsense we've got with AI is just nonsense. It's just the big tech bros making stuff up. And actually, that's another podcast, another day. But it's really exciting that I can see the chemists are now really excited to work with me. And now their emotional response from anger is now one of excitement. And how can we use it? And how can you help us make it more accessible, which is great.
So basically, as I understand, now chemists will be able to do more creative work and stop doing the terrible redundant work. But also, I have to say, I mean, it is very difficult to do synthesis. I mean, you know, how reactions can go very wrong. So like how exactly does a computer like take the samples in between? Or how exactly does it work?
Come and visit the lab and I will show you, is the first answer.
I would love to.
Well, come and visit. The second point is that there are reactions that you can do when you can basically make sure they work, and you can make sure they're like main railway lines to a city, right, to a chemical space. So you can get somewhere good, and then you can then basically explore from that. So what we try and do is make sure we have some certainty, some reproducibility, and we can make complicated molecules. But then, of course, the robots have inbuilt sensors. They know when things are going wrong. I have NMR machines and a fume hood, infrareds, and so on. So there's a lot that's happening. But I think the nice thing about computation is it will constrain, this seems counterintuitive, it will constrain the creativity of the chemist from all the reactions where they don't always work to ones that we have more certainty of working to build complexity to make the molecules they want, because more quickly, so we can make new dyes, new drugs, new fragrances. And that, I think, is a trick. It's the compromise between being completely like Leonardo da Vinci and painting the Sistine Chapel by hand, or using a kind of, some modern kind of art, a way of reproducing things and making, modern art stencils and so on. So it's a kind of that low volume, artisanal one-off to being able to replicate the thing and get deeper, because there are so many molecules to make. It will just blow your mind. And that's why chemists need digitization. It is the most important thing that I think I could do as a human being if I was trying to help chemistry. I mean, it may be terrible. The company may go bust. I might get fired. All these things are probably going to happen at some point, but at least I'm going to try.
Yeah, we are slowly approaching towards the end of the podcast. So maybe just a few or two final questions. When you look at the universe through the lens of chemistry and complexity, what do you think is the most surprising thing about how the matter organizes itself?
For me, the thing that I'm still kind of in awe of is that the idea that a complex molecule with a lack of symmetry, has a high assembly index that I can measure, and it's a real physical measurable with a molecule, and I kind of came up with that, and I'm just like, that's so cool.
I mean,
so that's what
it really is.
I mean, it might not be true, right? People still fighting with me in my group are like, oh, we don't think the assembly index is measurable, and I'm like, I think, look, here's the data. And they're like, we don't think, there's this, and this. There's still like, people criticizing in my team, who I think is super entertaining. And, it kind of normalizes me. But still, that's kind of cool. The universe is getting complicated somehow. And it looks like we can observe it happening. And for me to kind of put a new lens on that is really exciting. And I think there's three things that I'm really excited about. The first is observing the increase in the assembly index. The second is the realization that evolution requires bonds and combinatorial explosion to even start, right? And then the gateway from chemistry to biology is chemistry becoming more complex, and to a point where you have this self-sustaining system producing a genomic system. For me, is the answer to life in terms of how it emerges. Now we have to figure out how to understand it. And I'm like I said, I may be completely wrong. And I don't mean this as a get out clause. Like, there's one guy who keeps making random kind of, theories, kind of stealing what we're doing. And he doesn't understand it and saying, I could be wrong. I'm like, we know we're wrong. But we're less wrong than the other stuff, which means there's a step up, which helps us make a transition from this knowledge layer to the next one. And if I can be part of that, stand on the shoulder of giant, so that I can be a stepping stone to another thing. For me, that's fun.
Do you have any recommendation for any of the listeners that would be further interested in your work, or maybe something that you find really exciting besides your work that is happening or in support of your work, that you would say that is something to check out?
I am, as you might know, I'm a massive AI critic. And I love AI. This is the biggest kind of secret that people don't understand. I love AI. And what I think people should check out is the discrepancy between the correlations that AI is finding when we're looking in space and how humans can think and abstract. And I think the answer to human creativity and what is different about the human brain and the computer lies in discrepancy. And for me, I think people should think about that more deeply. Okay, use the tools. The tools are fun. They're quite good at faking stuff, so try and use them in a well-defined way. I think that's one thing. The other thing is I'm really excited about the fact that chemistry is becoming, on one side, people can start to do a little bit of philosophy, because chemists have before had to be just making stuff. So we can think about what does a bond mean? What are molecules? What does this mean in fundamental physics becoming technological? That is, I think, for an interesting thing for people to think about. And then also this notion of how can we construct minimal machines of molecules that can make other machines to make other machines to make a technology, so we could terraform Mars or other planets, right? It's like this way of creating matter that can create more matter, this like von Neumann replicator through chemistry. So even if the universe isn't a computer today, doesn't mean we can't turn it into a chemical computer tomorrow.
Good last sentence. But I do have to say, I definitely agree. I think chemistry definitely needs a little bit more philosophy thrown in there. Yeah.
For sure, yeah.
I think this was my last question. Do you have anything that you would like to add that I haven't addressed?
No, I think they were great questions. I loved answering them.
Yeah, okay, perfect. Then thank you very much for joining us today. And to our listeners, we hope you enjoyed this exploration of complexity and the origin of life with Lee Cronin. And we will be glad to hear your feedback.
Thank you very much.
Thank you very much.